In the last video, I started talking about active remote sensing technologies. This is where we actually get energy emitted from a sensor. That energy bounces off Earth's surface and comes back to the sensor. The first example we looked at was radar, which uses radio waves or microwaves, emits them usually from a satellite. Those radio waves bounce back to the satellite, which measures both the texture of the objects on the ground as well as their distance from that sensor, which gives you accurate elevation data. So now we have this more advanced technology that continues to develop. We keep developing new application areas, and this is called Lidar. So instead of radar, which is radio detection and ranging, Lidar refers to light detection and ranging. So most of that acronym, or like the root of the word, is actually the same thing, but now we're talking about little packets of light or laser pulses that are sent out from these sensors. These laser pulses reflect off something in the real world and bounce back to that sensor. It's a technology that's becoming a lot more prevalent in remote sensing, geography, environmental management, but it's actually a technology that's being developed in other areas as well. A big one that we're hearing about a lot about right now is with these autonomous vehicles. So Lidar is one of these technologies that allows vehicles to basically see what's going on in the world around them. If you have a vehicle that's equipped with Lidar technology, that vehicle can emit pulses of laser light, and by analyzing those returned pulses of light after they bounce off of things in the real world, algorithms within the system are able to define what those things are. In addition to these like really high-tech examples where we're looking at like the future of technology, we also have really important applications in the scientific community as well. So the example from the bottom right is using LiDAR mounted on an airplane to look at archaeology within the rainforest. So we've actually discovered buildings, agricultural systems, ramparts, ditches, all these like old archaeological pieces of ancient civilizations that would have been hidden by the forest canopy otherwise. So they're things that might even be hard to see because of all the undergrowth when you go into that forest from the ground. They'd definitely be hard to see if you're flying in an airplane over that area because of the canopy, but with LiDAR we can actually get this accurate on-the-ground elevation information, and we can put that information into some of these classification algorithms that allow us to actually define what these objects on the ground are. So in geosciences in general, LiDAR is really, really useful in creating high quality DEMs. You can get like really accurate, really high resolution elevation data at very large scales. Like in the example to the bottom right, you can actually like see drainage ditches that were built thousands of years ago because of how they differ in elevation from the areas around them. In an area where you thought everything may have been like of natural origin, if you see like patterns of human construction, you can tell that something different was going on there. But they're also useful in measuring the height of things, measuring biomass, so like how much actual plant material exists in an area of forest. Again, this is based primarily on elevation of an area, and we'll see how we get those measures of biomass in a little bit. Overall, it's become really important for studying not just like what the highly detailed surface model of Earth is, but also looking at, like we saw with that SAR interferometry, how we can assess very fine scale changes in elevation that are due to natural events or human events. So to show a couple examples, I found this really cool story map of how Washington State uses their high quality LiDAR data to assess natural hazards in a number of different ways all over the state. So this is a story map published by the state of Washington showing really cool geologic features that have basically been discovered because of LiDAR, or at least things that have more information about them released because of LiDAR, and how we can actually like measure or look at natural hazards, of which there are quite a few in Washington. So first here we have just a aerial photo of an area of forest in Washington. A lot of western Washington is made up of forests like this. You can't really see much going on that would be of note geologically here. But you'll get a different picture when you actually see the fine scale elevation differences within this scene at the ground level underneath these trees. And LiDAR lets you basically look through the trees and see what's present on the ground. So when we're able to look through those trees, we actually see all these landslides that have occurred there, and we might be able to predict where active landslides might occur in the future. You can see these fine scale elevation differences between what would have just been floodplain before and then areas that would have fallen from the nearby cliffs but then later would have been grown over by forest that would be difficult to detect even by walking around those areas of forest. In this case, we have evidence of a volcanic hazard. These are lava flows that came from previous volcanic eruptions. When we just look at the visual image like this, the aerial photo of this area, you can see like one big blob of lava. We don't really know if there have been like different volcanic eruptions over time that have created this, or if there's actually more evidence of different lava flows that are maybe older and have been grown over with more forest. Again, by looking at high quality LiDAR elevation data of the scene, we can see really fine scale differences, and it becomes really clear that there's been a number of different lava flows over time that have flowed through the same trajectory and kind of built on top of each other. So without that fine scale information, with something like that radar data from the satellite, you just get kind of like those larger pixels saying what the average elevation is in this area. You wouldn't be able to draw these fine boundaries of where different lava flows actually exist. Again, in this image, just a simple visual part of the spectrum image, just a normal photograph of Bainbridge Island. By looking at this image, there's like no indication that there's any fault in this area. But again, if you look at that LiDAR data and an image derived from LiDAR data, you get a really clear image of where this fault is. And here we see elevations surrounding Cape Disappointment. This is an area that's at risk of tsunamis. Basically, this part of the coastline is really exposed to just the Pacific in general. It's on a convergent plate boundary. Convergent plate boundaries, when they have like big movement and a big earthquake, these are usually the source of tsunamis. So if a big earthquake was to happen, you might want to identify where a tsunami might get to. And with this high resolution LiDAR-derived DEM, you can look at the areas that would be safe in a tsunami scenario based on like a certain size of earthquake and a certain size of tsunami. This is a pretty cool example too. In this case, it looks like you have a pretty narrow river channel. There's a little bit of braiding, not a ton of braiding, and it's mostly surrounded by forest. Looks like a pretty standard river. But again, by analyzing this high resolution LiDAR data, you can actually see that over time there have been many more channels that are visible now. Most of them have just been covered in forest now. So here we see like the main channel is biggest and brightest, but if you look at really small scale elevation changes, you can see tons of previous channels that no longer are clear on the landscape. So LiDAR is a widely used technology. The number of applications for LiDAR continues to grow. But now let's turn our attention a little bit towards how LiDAR actually works. So again, LiDAR stands for light detection and ranging, and it essentially functions by having a unit that emits a laser pulse or a pulse of light and measuring the time it takes for the pulse to return to the scanner. But of course, it doesn't just release one pulse. It releases millions of pulses over time, and with those millions of pulses, you can get that high resolution elevation data as well as some other valuable data about what's on the ground. So if you're shooting laser pulses out from this LiDAR unit, the way that it computes elevation is by calculating the distance between the unit and the ground. So basically the time it takes for that laser pulse to make it from the LiDAR unit to the ground, to bounce off the ground, make it back to the LiDAR unit, that's measured and converted into a distance, a very accurate distance from where that LiDAR unit was at a specific time. So it's a fairly simple equation. Light beams travel at a known speed, which is the speed of light. And that's just multiplied by the time of the flight of that laser pulse, of that photon. And then that's divided by 2, because of course it's going to the ground and then back again. So after distance is calculated for that point can be placed in 3-dimensional space, corresponding to the location of where that laser beam bounced off that thing on the ground that it was detecting. So more than just that LiDAR unit on something like an airplane or a drone is required for LiDAR to actually work. So the main thing is that the time it takes for that pulse to bounce off the ground is measured by the actual laser scanner that emits and receives pulses. But to really get high accuracy in locating those points, you also need a very accurate understanding of where the plane is. So there's a couple other parts besides just that LiDAR scanner or laser scanner. So you need really high accuracy GPS to find latitude, longitude, and altitude of the plane at every given point in time when all those laser pulses are emitted and detected once again. These give you X, Y, and Z coordinates of where the plane is that can help in placing that point on the ground for where that laser pulse actually bounced off of a thing. There's also something called the Inertial Measurement Unit, or the IMU, that's part of a LiDAR scanner system. This determines the way that the aircraft is oriented. the pitch, roll, and yaw of the airplane. If it's kind of like tilted sideways or tilted front to back, the location of the return has to be corrected for what the plane was actually doing at that point in time. And then there also has to be an onboard computer that can adjust for all these variables, correct the location based on like the GPS points, the calculated distance that laser pulse bounced off of, and also the angle that the points are being emitted and received from. So there's all kinds of like sophisticated calculations going on in real time as these LiDAR flights are operating. So as the platform that's collecting this LiDAR data is moving over the landscape, there's either a rotating or an oscillating mirror that directs these laser pulses from side to side, covering a swath of a specific width. This results in a zigzag pattern of the actual returns or the actual detection of things on the ground. And it also means that scan angle has to be taken into account. So when you're computing the distance that laser pulse travels from the plane to the ground and back again, it's going to be a little further if the plane is shooting this laser pulse off to the side, and that has to be brought into the algorithms. The total number of pulses per second differs based on LiDAR unit. This is the actual number of little laser pulses that shot out of that plane, and that can range from about 50,000 to 200,000 pulses per second. So that's really a lot of pulses that results in a lot of potential returns. So you can really cover the ground with a lot of data and get a lot of reflected returns coming back to the LiDAR unit. So a LiDAR unit emits a laser pulse that bounces off something and makes it back to the sensor. That returned energy that the sensor reads is called a LiDAR return. That's all the energy bounced back from a single pulse. But why LiDAR is super useful, especially modern LiDAR, is that these newer units can read multiple returns instead of just one return. So you can actually send out one pulse and get multiple returns from different locations based on that one pulse. So imagine you're standing under a tree and you look up. The tree itself isn't penetrable to light. However, some light from the sun comes through the branches and through the leaves. So the same thing happens with LiDAR energy. If you have a pulse of light coming down from the sensor, some of it will hit the leaves and bounce back. Some of it might just kind of skirt the side of the leaf and hit a stem or a branch, just like right under that area of leaf, and bounce back. Some of that might hit like a fern underneath that tree and then bounce back. And finally, some of it might hit the ground. So you can actually get multiple returns. The entire surface area of that pulse, parts of it hit different objects on its way down to the ground and get reflected back from those objects. So that means that one pulse can result in different returned information and a number of different distances from the plane or the drone that actually has the LiDAR unit. So looking at the image to the right, we have that orange line that's basically depicting the trajectory of a LiDAR pulse. Some of that pulse will hit the top of that tree and bounce back. Some will hit a branch a little further down, that second return, and bounce back. Some will hit the tree underneath and bounce back, and some of it ultimately hits the ground and bounces back. Each of these will come back to the LiDAR unit as a separate return, so you'll actually get data on these different levels or different elevations along this single trajectory for that single LiDAR pulse. All right, so a raw LiDAR data set includes all these millions of points that make up all those different returns from the LiDAR. So you have a plane or a drone flying over a location, shooting out those laser beams, waiting for those pulses to bounce back. You'll end up with many, many, many returns. Each return will show up in what's called a LiDAR point cloud. A raw LiDAR point cloud will look like that image at the bottom left. Each one of these is a little point that exists in space that has not just X and Y data, that might be like latitude and longitude or something, an XY in a projected coordinate system, but you also have that Z value of elevation for that return. They're already geo-referenced because you have that onboard GPS, so you don't have to geo-reference it like if you had like a raw aerial photo. All these points, just by definition, already are geo-referenced and already are located in space. But you can actually get a lot more information from LiDAR than just the elevation of each of these point clouds. You can get a little bit more information for each of these points that make up the point cloud. You can get the source of the point, so like which flight or which path flown by a specific flight this point came from. Which number of return is it? Is it that first return, which would be like the first thing that pulse hits as it's making its way down from where it was emitted? Or is it the fourth return, which is like the furthest down thing? That last return's usually like the ground itself before the laser pulse made it back up to the plane. Then you can also have data on intensity. How much of that return was reflected, how intense was that return. So all these different pieces of information can be visualized as they are on the right, and you actually start to get information from this raw point cloud about the scene that you're looking at. Points colored by elevation, you already get some pretty specific differentiation between like the ground in yellow and tops of trees and tops of buildings that appear in like purples and pinks. Colored by intensity, things like trees, you don't get as strong of a return because only a portion of that pulse is going to be returned from hitting the tree. A lot of times, like again, if a pulse hits a tree, some of that pulse carries down towards the ground. You can get points colored by return number at the far right in the middle. That can help show you if there's something like a tree where you can get like multiple returns at once near that tree versus something like a building or just like a field where you're probably going to get like one return overall. Points by flight source is in the bottom left. This shows that in this area we're looking at, there are actually two different flights that make up that data together. If you combine a couple of these things, again, you can get like a pretty good look at what that area actually looks like, even though you just started with a bunch of points. So here we have intensity and elevation data displayed together. Now you can really start to see the difference between just like a road, a field, trees, and buildings. So again, LiDAR data in kind of its raw form or natural form comes as one of these point clouds. You don't actually get a raster. We usually end up converting LiDAR data to a raster because it's easier to use with other types of data. And that means that there isn't exactly a set spatial resolution to LiDAR data. But the accuracy of the output that's kind of like analogous to resolution is related to pulse density. So that's how many pulses there are per on the ground area. So do you have like 10 pulses in a meter squared, or do you have 100 pulses in a meter squared? That'll give you different quality of data because you have like more coverage with those pulses or less coverage with those pulses. So this density of pulses is actually controlled by several factors. You can have the same type of LiDAR unit employed in a different way that'll give you this different resolution or different quality or accuracy of your output data. So a big one is aircraft speed. If a plane's flying really fast, fewer of those pulses make it to a given point on the ground, but you will cover more area in total. Then also altitude. If you're higher up, that oscillating mirror that's like spreading those pulses to different areas on the ground, that's going to cover more on the ground area, which means there's going to be fewer pulses per area on the ground if you're like really high up. Pulse emission rate is a big one. That can differ by like the actual LiDAR unit you're using. So you can actually send out more pulses or fewer pulses based on what the LiDAR unit is. Current systems are capable of around 20 plus pulses per square meter, but even then when you have like high coverage, the pulses aren't evenly spaced. So again, there isn't really like a well-defined resolution that relates to LiDAR data, but you do get different quality and different accuracy based on the density of these points. That's demonstrated in the figure to the right. There's kind of a pretty clear line between areas where we have density of only 1 point per meter squared and density of 2 points per meter squared. If we derive products from that, kind of conduct some analysis on this data, the area where we have like twice as many points per area is going to give us higher quality output data than where we only have 1 point per meter squared. There's going to have to be more interpolation and more kind of guessing at those in-between areas when we have fewer points to base like the construction of an elevation surface on. Just like when we're talking about like other types of remote sensing data, sometimes you don't need high resolution, and it's actually like a worthwhile trade-off to just use lower resolution or lower point density but be able to cover more area. Other applications you want like as many points as possible to get higher accuracy. So for LiDAR, really like the number of points you need per area is really strongly correlated to like what use you're actually going to have for that data. So if you're creating 3D models of a city, of like cars in the city, of trees, of plants, of buildings, then you want that like maximum quality 10 points per meter squared data. You'd want to have like a really near the ground flight with a slow flying aircraft or drone, and you'd want like a high pulse emission rate. However, on the other end, if you're just trying to create like a DEM over a very large area, like remember that US 3D elevation program, they're trying to make like a DEM nationally with LiDAR at a 1 meter resolution scale. So once they process the data, they'll make a raster of 1 meter resolution. You don't need a whole lot of points for to create that kind of a DEM. So for a basic surface model, you might just need like 1 point per meter squared. You might have other requirements in between. So a basic 3D model, You might want 5 to 10 points per meter squared. At the other end, 1 to 2 points per meter squared might be useful for like flood modeling. So you want like a little higher resolution than just like a basic surface model to see where that water flows, but you don't need like super high resolution. As mentioned before, much of the utility of LiDAR data comes from like this really high resolution, highly accurate elevation data, but you actually get more information than that, as I mentioned on the earlier slide. So intensity of the return is also recorded during data collection, and this is really useful in helping with feature classification and extracting individual features using those object-based methods we looked at before. Data ends up black and white, like a single band of remote sensing data, but you can actually scale these data based on how well they reflect that pulse of light. So every substance has these properties of like absorption, reflectance, scattering of light, that kind of thing. And they do this with a laser pulse as well. So if you get something that has like really good reflectivity, it'll just take that laser pulse and the laser pulse will completely bounce back 100% back up to the scanner. But other things might absorb that laser pulse, so it won't actually reflect really at all, or that light that hits the ground or an object might be scattered as well. You have all these different things that we talked about before that can happen to one of these laser pulses once it hits an object. So something like white paper or snow has like really high reflectivity. If you shine a laser at white paper, the light from that laser basically reflects back. You can see it really clearly. But if you shine like a laser pointer into black neoprene, like imagine a wetsuit is made of black neoprene, or into like a bowl of water, it basically gets absorbed. It doesn't reflect back out. So the same thing happens with laser pulses from a LiDAR unit. Those laser pulses can actually get absorbed by some things like asphalt, black surfaces, dark surfaces, or water, where the laser light can actually penetrate into the water a ways. LiDAR data could potentially come from a variety of different file types. Earlier, ASCII was the standard, but this wasn't very good at storing attributes, so more recently what's called the LAS dataset was developed by the ASPRS, the American Society for Photogrammetry and Remote Sensing, to contain all the information that really needed to be encoded with one of these LiDAR point cloud datasets. So it's a binary type of dataset, so it works a lot faster than ASCII, which had to store a lot of different characters. And it also contains a header, which holds a wide variety of metadata. So that header is visible to the right here, that has a lot more information about that data set than just like a text file or just the points themselves. It's also a useful data set type because it's flexible as to what extra variables or fields can be held in one of these data sets. Things like reflectivity, like we looked at before, or return number. And in the file itself, the X, Y, Z data, along with these different attributes for each of these returns, is stored for each return. Ultimately, what most people want to do with one of these LiDAR datasets, with one of these point clouds, is to convert it to an elevation model. There's a couple different elevation models. I'll talk about that on the next slide, but there's actually a couple different workflows in converting one of these point clouds to a DEM or a DTM or a DSM. Again, I'll talk about the difference in a second. So one way to do this is after you import these raw point clouds, you'd create one of these triangulated irregular networks, basically a surface model linking these points together, and then converting that TIN or TIN, triangulated irregular network, to a raster surface model. So that workflow would look like the sequence at the bottom. We have several different LiDAR datasets. Each one of those is going to be a point cloud. In ArcGIS, you can convert those to a multi-point feature class, make a terrain dataset out of that using a triangulated irregular network, and then convert that to a raster. In ArcGIS Pro, this workflow has been simplified quite a bit. So you can actually link together all these different point clouds from different flights. So you might have, instead of these LiDAR 1 through 6, you can use one tool to just link these together into an ArcGIS file type that is this linked together LiDAR dataset for one entire study area. And then there are actually specific tools now that can convert that LiDAR dataset compiled in ArcGIS into one of these multiple different types of elevation rasters that we'll look at on the next slide. So the second workflow is actually what you're doing in the lab. You're going to create multiple elevation rasters from LiDAR files. In ArcGIS Pro, it's a little bit easier than is shown on this slide. So a few times now I've mentioned these different outputs that you can get from a LiDAR point cloud. The different types of outputs relate to which returns you use, if you use the first returns or last returns. Remember, the first return is going to be that first thing that a LiDAR pulse hits off of and bounces back to the LiDAR sensor from. The last return is going to be the last thing that one of those laser pulses hits before it turns around and makes its way back to the sensor. That means first returns, if you use all first returns, make a surface out of that, make a raster out of that, you're going to basically get like that first level of thing, or the highest elevation thing in your entire study area that would be struck by one of those laser pulses. If you're using the last returns, you're going to get a better idea of where the ground is. Usually the last thing a laser pulse hits is going to be the ground. There are a few exceptions. In a lot of cases, you need to process the data a little more to identify things like the top of a building, because the top of a building would be like a first pulse and a last pulse, even though it's not the ground. In a forest area, for example, you can get very clear differentiation between like the top of a tree and the actual ground. So there's a little bit of disagreement regarding terminology, but we have these three different types of surfaces that relate to elevation in an area. First, we have digital elevation model. We've talked about this quite a bit already. This is a raster with z values containing elevation that usually refers to the Earth's surface. The second one of these acronyms is DTM, which stands for Digital Terrain Model. This is actually used interchangeably with DEM a lot of the time, but Digital Terrain Model is a little more specific and more often used with this LiDAR data. A digital terrain model specifically relates to like the actual structure of the Earth. Digital elevation models, if you're looking at like worse resolution, a lot of times some of these like finer scale differences that you would want to consider in a DTM are ignored when you're looking at a DEM. Finally, a digital surface model, or the DSM, includes the heights of objects, things like trees, buildings, etc. This would be that result from looking at all the first returns together and ignoring where the ground actually is. So when you're working with LiDAR data, usually we use the second two of these acronyms to refer to basically the actual ground for a digital terrain model, or DTM. That's like the Earth's surface, top of an area of water, or the actual ground itself. A DSM, or digital surface model, is that layer of the first return, so including the tops of trees, tops of buildings. And as we'll see in the lab, you can actually subtract one from the other to get an estimate of the height of things that sit upon the ground. So that's a pretty cool use of these LiDAR elevation models. And as an example of each of these, the top right, that would be a digital terrain model. We're looking at like the raw Earth surface. You can see mountains in red, or at least larger hills, areas of water or lower elevation areas in blue, and green is just kind of like a flat plain that's pretty close to sea level. Digital surface model would be the bottom right. Here you can actually really clearly make out buildings, in some areas trees, other things that like are built on top of Earth itself. You can actually see the elevation of those things. Beyond just representing the elevation of the ground or the elevation of things that sit on the ground, there's a few different analysis methods that can be undertaken. So there's several different equations that can be used to learn about phenomena on the ground. Again, if you subtract the last returns from the first, then you get height of objects on the ground. So you can get like the height of a tree. In a forest area, for instance, you might take like the average height of an area of forest and use that to compute biomass, or how much actual plant material there is in that area. That also might help you compute net primary productivity, which is like the amount of photosynthesis happening in an area. There are also methods for segmenting and classifying data. So if you remember when we were talking about classification last time, classification is basically like saying what each of these things is. And segmenting them is actually like creating individual items out of a point cloud or out of a raster area. So you can take information on that return profile. So things like buildings will only have one return, whereas an area that has a tree might have multiple returns. You can also take information on brightness, like we saw before. An object like snow reflects the returns really well, whereas something like the leaf of a tree might not reflect it very well. You also might get information on texture. So if you're getting like a lot of close by returns, having slightly different elevation, you're going to have like a much rougher texture than if along a surface all the returns are along the same plane. So with all these things, you can actually like create rules like we looked at before, using things like random forests or these different classification algorithms to actually clump together objects and say like this thing is a tree, this thing is a car, or this thing is a building. Finally, like we talked about a couple times ago when we were talking about surface methods, you can create contours. So contours are those lines of equal elevation drawn on the landscape. You can get like really high resolution contours showing change in elevation using one of these digital terrain models specifically. So LiDAR is really cool, really quickly improving technology that has a lot of application potential in the real world. One of the hurdles now is that it's actually expensive to collect this data, and collection usually only occurs over a small area. So you still need drones or airplanes to collect it. We're not putting LiDAR units on satellites, so there's like no around-the-clock continuous collection of LiDAR data. You actually have to like pay to have a flight to collect LiDAR data for your location, or launch a very expensive drone with a LiDAR unit on it. So as these things get cheaper and more available, we'll get more and more LiDAR data to play with. But right now, it's an important technique to just have the basics of, for if you're working for a city or a government, a lot of times they're collecting a lot of LiDAR data now and processing a lot of that LiDAR data.